The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
This is just intended to be sort of a brief update of background of the recent DoD research and potential future updates to the UFC 33402 blast design guidance. And the disclaimer here at the bottom, this presentation really only discusses DoD research that either NAVFAC, EXWC, my command, my organization, or DDSB, Bill's organization, are involved in. First, as I'm sure has been discussed, UFC 33402 provides design guidance for structures to resist the effects of accidental explosions. The requirements to design UFC 33402 are typically triggered when there's some explosive safety minimum stand-up distance not satisfied. This could be applied to operators, explosive workers, or perhaps unrelated buildings on the base itself. And just a huge caveat, the deviations are not permitted for off-base exposure. Reinforced concrete is the preferred construction material for blast-resistant design. You get mass, strength, ductility, and penetration resistance, which I definitely won't go into the penetration resistance portion of this for this presentation. But on top of that, there's cost, constructability, and maintainability. Just not to confuse the matter, there's lots of anti-terrorism force protection, ATFP blast design. This is not what I'll be discussing today. There are ATFP requirements for DoD facilities, but I just want to reiterate that explosive safety structural design requirements are more stringent due to a known quantity of explosives at a known distance, so it's much more of a known loading scenario than, say, the ATFP environment. So the first topic in this presentation is internal blast loading. Just a general background, shock loading parameters from a detonation are defined as a function of scale distance. This is the cube root scaling law, and what you see here is the graphic up there on the right. You know your scale distance, and you can quantify the pressure, the impulse, the time history, all those parameters necessary for defining the blast loading from that. For internal loading, you don't just get an open air explosion, but the shock load is amplified from reflections within the structure. And on top of that, you get from the effects of the high temperatures and the release of gaseous products, you developed a internal gas pressure buildup, referred to here as the gas load. There was software called Shock and Frange developed by the DoD in the 1980s. That are used to automate this procedure, and the graphic here on the bottom left just refers to for a given loading scenario, for a given gas pressure, for a given internal volume, for a given venting. It just kind of gives you a feel for the curves you have to look up to calculate from the manual itself the gas pressure and the shock loading in its environment. In Shock and Frange, these two pieces of software were developed to automate this procedure. Recently, we've developed a piece of software called ConBlast to replace Shock and Frange. It provides improvements to the existing methodology, improvements to the shock load calculation, additional enhanced capabilities, multiple venting panels. And again, this is open distribution. It's a graphical user interface. So you get a feedback from what your input files are. The previous versions of Shock and Frange were DOS-based, not that easy to use. And so this is just an improvement of the code, or improvement of the software code that goes to in conjunction with UFC 33402 design methodology. I do caveat the software is still beta version. It will be finalized in the near future. And it is a drag and drop, no installation required. Additionally, another aspect of internal blast load generation that has provided issues in the past for blast design is lab quantities. Here we're referring to lab quantities as less than 100 grams. It's sort of that 100 grams is a bit of an arbitrary value. 10 figures, 10 toes, base 10 math. So we get a nice round number like 100 grams. But this is really referring to smaller quantities. So the issue is the blast load predictions, the Kingery-Bolmatch curves, are really geared more towards larger quantities of explosives. And so it sort of falls apart. We get really, really conservative predictions of internal blast loads for these small quantities. So the DoD's investing very preliminary stages in a test program to quantify better predictions of internal blast loads for lab quantities, both from the shock standpoint and the gas pressure standpoint. And yeah, the desired goal is to generate more appropriate blast loading predictions for the small quantities. And getting a reduction in demand loads and a more economical design for these facilities that require them. The next topic here is rebar technologies. By that I just mean mechanical couplers, headed rebar, and it's been a bit of a topic here, I think, at the sessions I've attended at ACI. And the advantage of the couplers and headed rebar, you get improved constructability, enhanced concrete quality, you get better consolidation, you don't have such congestion due to the massive amount of reinforcement. I mean, that's typically a problem for our containment facilities on DoD blast design. You get heavy amounts of reinforcement in there, and consolidation in concrete is definitely a problem. You simplify the rebar detailing, and I think there's this other bullet here, the more efficient load transfer mechanism. That's an important point, which I'll talk to in a second. And the current efforts I'll discuss here. There's lots of other efforts I know that the previous presentation discussed, but the current efforts here leveraged previous headed rebar threaded coupler testing of these highly dynamic load environments. Just want to emphasize it's a different load environment than is typically seen in the ACI specs. And the testing portion was funded by the Air Force Civil Engineering Center at Tyndall Air Force Base, and the analysis and modeling was conducted by two persons in my office, Dr. Mike Esterly and Neha Chhabra. There was a test that was conducted. It was not for the primary purpose of this headed rebar and mechanical couplers for these internal walls, but the intent was to generate more data, as much data as possible from these tests. So the test article consisted of a reinforced concrete wall of conventional rebar detailing, I'll refer to it as the baseline RC wall, and there was another reinforced concrete wall, which I'll discuss more in a second, using thread rebar couplers and headed rebar that will be referred to as the test reinforced concrete wall. The test article itself represented an internal blast room, including sufficient vent area, a door, which I'll show in a second from the spec, gives some amount of venting, so it wasn't in totally a confined loading scenario. There was I'll show the baseline test in a second. Due to limited deformation, the decision was made to do a couple follow-on tests to again test the full capacity of the headed rebar in the couplers, trying to get as much response as possible in comparison from the baseline wall to the test wall. All responses measured. The performance of the baseline RC wall and the test RC wall were compared. So this just shows you a spec of the room setup. It was a 20 foot by 20 foot by 12 foot. That was the internal donor room. From the explosive weight scenario, I can't go into too much detail here, but there was a baseline demonstration and a test one. There's minimal response. Test one increased the charge weight, and due to the response of test one, we increased the charge weight further for test two. It was detonated at the floor in the center of the donor room, and there was this doorway-sized vent area right there, and there were 4 witness rooms. And I think the next figure gives a little more detail to the test setup. So up top here, where there's a composite steel stud wall, which we will not discuss in this presentation. And here we had the test wall, and over here was the baseline wall. On both the test wall and baseline wall, there's 3 sides supported, so this is a free edge here, free edge here. 2-way bending, fixed on 3 sides as I mentioned, and the top, bottom, and corner connection details were tested. The center line of the structure here, there's a reinforcement detailing change. So again, right here, we have the conventional wall, and this side of the door, the corner, all parts of it, was testing the test wall. A little more detail about the walls themselves. They're 1 foot thick, 12 foot high, 20 foot length, 5,000 PSI concrete. It was number 75 rebar, number 6s at 8 inches each way, each face, number 4 single leg stirrups. For the test wall itself, used Dewey dag thread rebar couplers, and the steel plates on the heads were nominally chosen as a 3/4 inch by 4 inch by 4 inch with locking nuts. This just gives you some detail in terms of the actually connection details from the baseline wall versus the test wall. We actually see much more congestion in a lot of our internal design scenarios. This is just typical reinforced connections you see for the conventional reinforcement, but a lot of times we have much more congestion with respect to the joints, and that is really a problem. It's a problem to construct, it's a problem to build, it's a problem for quality, and this just gives you a feel for some level of the relief provided by couplers as well as headed rebars in the joints and detailing. Just a little information on the pressure gauges, the instrumentation themselves. Inside the donor room, we had 9 pressure transducers on each of the walls, the test wall as well as the baseline wall and the steel stud wall, which I won't discuss here. There was also displacement gauges on the back of the wall to get the full wall response, not just the middle of the wall itself, but I'll be discussing maximum response in terms of the center wall deflection. And there was also high-speed video on the back side of each of the walls. So there was the baseline demonstration, which again, as I mentioned, was not for entirely for defining the efficacy of these connection details. There was other purposes of it as well. But here you see a still shot from the test structure. This represents the door. Obviously, you can see the venting coming out the front side of the door. And there's very minimal displacement. These are maximum displacement values listed for the baseline demonstration. It wasn't quite elastic response, but it was almost elastic response. So I think it's fair to move on from here and saying that there's minimal to no deformation from the walls themselves. And ultimately, the limiting factor in terms of the load we can put inside the room is from the roof. The roof itself is much weaker than the walls, lower resistance, less stiffness. So I think we could put as much explosives as we wanted into the structure. Well, it's not entirely true to the range limitations, but we could put a lot of load inside the structure. But all that was going to happen was you blow off the roof, and so that was a limiting factor in terms of the design charge weight for test 1 and test 2. Here's the results of test 1. You can see the displacement is very minimal. Support rotation is less than 1 degrees. The design methodology in UFC 33402 would predict greater than 2 degrees support rotation here, so it's a design manual. We know we're conservative, but that's okay. But I think one of the important points to take away from here is that the test wall, again, the header rebar and couplers, had less deformation than the conventional construction, the conventional rebar detailing from the baseline wall. The 0.72 degree support rotation advised the 0.53 degree support rotation. So because of the limited deflection, limited response, we felt that we could do another test here. So we did test 2, and it's kind of hard to see here the crack pattern, but here this shows a picture of the front of the wall. Very minimal damage on the side of the wall here. You can see the cracking here on the free edge, and you get the typical yield line pattern. It's probably easier to see in the presentation itself if I see the screen here. So here's the baseline RC wall, and one thing to note is that this is the test RC wall, and on the baseline RC wall we get much more cracking than we do from the test wall. Much more cracking in the conventional rebar detailing versus the header rebar and coupler wall. Here shows a photo post-test of the reinforced concrete roof. We get lots of failure in the compression zones. We could test this one more time, but I think it's at incipient failure for all intents and purposes. Here's a summary of the test 2 results. So again, test 2 provided even more internal loading than test 1, which provided more internal loading than the baseline test. And again, we see the same trend here that for the baseline wall, for just test 2 itself, this is just the test 2 results, and this over here shows the cumulative results. For the test 2 results, the baseline walls deflect about 2 degrees versus the test wall itself at 1.3 degrees. Again, just some nominal figures for the pressure time history as well as the displacement time history of these walls. And again, an important takeaway here is that the header rebar and couplers wall, the test wall, had a much better performance than the baseline wall. So I think just in terms of tying up this discussion point, cumulative deformation of the baseline RC wall exceeded 2 degrees support rotation. That's test 1 plus 2 response. The deformation in the test wall did not. It's reasonable to assert that the reinforced concrete wall with the header rebar and mechanical coupler connections in this configuration perform much better than the conventional rebar detailing of the wall. So I think the header rebar deformed less under these similar loads, probably due to better fixity at the supports, better connection, better load transfer. The overall total deformation of the joint, the wall deformation plus the roof deformation, is about 8 degrees. So on average, the joint deformation, the joint itself demonstrated sufficient detailing to achieve support rotations equal to about 4 degrees. And the wall response, as mentioned previously, the wall response from the analysis using UFC 33402 predicted displacements far exceeding the measurements we got in 2 degrees. We did a bit of numerical modeling, or actually Dr. Mike Esterly and Nehat Chabra, who work in my office, did quite a bit of numerical modeling for predictions of these test scenarios. And not as conservative as UFC 33402 predictions, but the numerical modeling using LS-DYNA did predict a bit more response than was seen in the actual test configuration. So what can we conclude from this? I think it's fair from the test conclusions. We conclude from the test that the performance of the wall, headed rebar, and mechanical couplers exceeded that of the wall of the conventional detailing. And the wall with the headed rebar and mechanical couplers demonstrated personnel protection up to support rotations equal to 2 degrees. In explosive safety, that personnel protection is key because that corresponds with the 2 degree support rotation for reinforced concrete members. And I think that's probably, for the most part, where we're looking at applying these in our blast design guidance, the 2 degree support rotation and less. I think it's fair to say that development of criteria for blast design guidance has other nuances that exceed what industry standards are looking to achieve. We have substantial deformation. If we move beyond the 2-degree support rotation, we get substantial deformation. We have cyclical loading, so this thing responds, you get a tremendous amount of compression in the header rebar mechanical couplers during the response phase, the rebound. Dynamic material strength increases, which is somewhat defined with these systems. So it's premature to validate the use for all designs, but I think it's quite promising in my opinion. And the indications are that the use of header rebars is satisfactory in this condition, given that we design for less than 2-degree support rotation. The second bullet here is somewhat key. The header rebar system can develop equivalent stress-strain relationships to that of the undeformed bar, or I guess to hooks, excuse me. And the header rebar connection details are in accordance with ACI. The desire is to go into further testing to validate use of header rebar in all configurations. We imagine that it's probably just going to be limited to the 2-degree support rotation or less. That's where we see the biggest use of this system. The last topic I'll be discussing here is debris impact perforation. Project Eskimo, the Explosive Safety Knowledge Improvement Operation Redux, is the DDSB's long-term explosive safety testing initiative. A significant focus of that test program has gone towards prediction of secondary debris hazards. Primary debris is typically fragmentation from the casing of weapons. Secondary debris is referred to as you have a bunch of ammunition in a storehouse or a cover magazine or what have you, and that building itself becomes a debris hazard. You generate lots of concrete and steel debris, primarily concrete, from an internal detonation there. And so that's been a significant focus of the Project Eskimo test program. One of the test series within Project Eskimo is SPIDER. It's the DoD, so you have to have a cool acronym for everything. I'm not sure if SPIDER's cool, but this is the Science Panel Impact Debris Evaluation Review. It is a test series within Project Eskimo, and it's looking at perforation of conventional construction, conventional wall, conventional roof, different types to impact and perforation of steel and concrete debris. The targets in the SPIDER test series consisted of reinforced concrete walls, reinforced concrete roofs, CMU walls, both grouted and ungrouted, and steel panels and wood panels. SPIDER 1 was conducted about 10 years ago at Emertech in New Mexico. SPIDER 2 was conducted in 2009 at Redstone Test Center in Huntsville, Alabama. And we're currently conducting SPIDER 3 right now, and that's being conducted at Redstone Test Center in Huntsville, Alabama. We completed Phase 1 2 months ago, and Phase 2 is scheduled to be completed at the end of this month, probably about 2 or 3 weeks testing period of Phase 2. Again, I won't go into tremendous detail about the program itself, but if you have any questions, any more information you desire, please come talk to me after this session. So here's a couple slides just to give you a feel for the SPIDER 3 test program itself. SPIDER 1 and 2, again, looked at spherical concrete and spherical steel impactors. SPIDER 3 is looking at cylindrical impactors. Not truly cylinders, but they sort of have a hemispherical head on top. Looking at length to diameter ratios of 6 and 2. Looking at various mass and velocities and trying to develop the perforation thresholds for each of these components. On the explosive safety side, in terms of blast consequence and risk prediction models, we define hazards to persons largely in terms of kinetic energy for blunt force trauma type impacts. So a lot of the work here is to define the perforation thresholds in terms of kinetic energy. But we also use mass and velocity as independent variables because, again, depending upon the mass and velocity, you have a couple different regimes for perforation as well as injury to persons. There's a kinetic energy regime. If you get smaller masses at higher velocities, you get something that's more along the lines of V to the fourth, sort of ballistics penetration developed regime for injury and fatality. And for the larger debris masses, it's typically more of a function of momentum or just velocity itself. So here we have a cylindrical steel impactor LRVD of 6, and here we get impact velocity, and during the tests themselves we're measuring a bunch of aspects of it. We have high-speed video on the front side as well as the back side to determine the impact velocity as well as the residual velocity. We used a high-speed Doppler on the front end to quantify the impact velocity, but there were some issues with the Doppler itself, so we found that the high-speed video was a much better mechanism to determine impact velocity, given that you calibrate the camera to the direct path where the impactor is hitting the target. So we determine perforation resistance, perforation threshold, as well as residual velocity for these targets. As you can see from the picture on the right, we use multiple impacts on a single target, but we do our best to, well, that's for cost purposes, but we do our best to hit a clean, if you will, target area within the target itself. So we typically get maybe 5 shots on a given target for these reinforced concrete walls, which are about 8 or 9 feet squared, I think. Here shows you a picture of the CMU wall target. It shows a picture on the front, a small on the back side. I think this particular wall was reinforced and grouted every other cell. So you see the spall coming off the backside of the target itself. Again, on the CMU wall, we've impacted both reinforced and grouted cells as well as ungrouted cells to determine the perforation resistance for each of those. We had lots of good data from the Spider 2 test series for the conventional wall perforation resistance. The Spider 3, again, we used these cylindrical impactors and higher velocities to get more information. This shot you see here, you can see the L over D of 2, sort of more of a stout impactor. This particular shot had a 2.3 pound impactor. In here, I won't go into too much more detail, but here's just some shots from the recent test series of Spider 3 for the steel panel targets. The perforation with the steel panels is really characterized by shear punching failure. And so what happens, it really depends on where you hit the panel. If you hit one of the ridges, you initiate the shear punching failure in the earlier response time, and you get a minimal decrease in velocity when perforation does occur. But if there is no early time shear punching failure, there's really a large amount of energy dissipation via membrane response. So it's really sort of I guess in ways a binary response for the panels themselves in terms of do they punch or not, and if they do, what the residual velocity is. There's just a couple slides here showing some information regarding the LSI of the computer modeling for the predictions that were done for this test series. So we did a small amount of modeling, validation, I guess fine-tuning